In the mathematical fields of general topology and descriptive set theory, a meager set is a set that, considered as a subset of a topological space, is in a precise sense small or negligible. The meager subsets of a fixed space form an ideal of subsets, that is, any subset of a meager set is meager, and the union of countably many meager sets is meager. General topologists use the term bare space to refer to a broad class of topological spaces on which the notion of meager set is not trivial. Descriptive set theorists mostly study meager sets as subsets of the real numbers, or more generally any Polish space, and reserve the term bare space for one particular Polish space. The complement of a meager set is a comeager set or residual set. Definition: given a topological space X, a subset A of X is meager if it can be expressed as the union of countably many nowhere-dense subsets of X. Dually, a comeager set is one whose complement is meager, or equivalently, the intersection of countably many sets with dense interiors. A subset B of X is nowhere dense if there is no neighborhood on which B is dense. For any non-empty open set U in X, there is a non-empty open set V contained in U such that V and B are disjoint. The complement of a nowhere-dense set is a dense set. More precisely, the complement of a nowhere-dense set is a set with dense interior. Not every dense set has a nowhere-dense complement. The complement of a dense set can have nowhere-dense and dense regions. Relation to Borel hierarchy: just as a nowhere-dense subset need not be closed, but is always contained in a closed nowhere-dense subset, a meager set need not be an F-sigma set, but is always contained in an F-sigma set made from nowhere-dense sets. Dually, just as the complement of a nowhere-dense set need not be open, but has a dense interior, a comeager set need not be a G-delta set, but contains a dense G-delta set formed from dense open sets. Terminology: a meager set is also called a set of first category, a non-meager set is also called a set of second category. Second category does not mean comeager. A set may be neither meager nor comeager. Properties: any subset of a meager set is meager, any superset of a comeager set is comeager. The union of countably many meager sets is also meager. The intersection of countably many comeager sets is comeager. This follows from the fact that a countable union of countable sets is countable. Banach category theorem: in any space X, the union of any family of open sets of the first category is of the first category. Banach-Mazur game. Meager sets have a useful alternative characterization in terms of the Banach-Mazur game. If is a topological space, is a family of subsets of which have non-empty interior such that every non-empty open set has a subset in, and is any subset of, then there is a Banach-Mazur game corresponding to, in the Banach-Mazur game, two players, and alternate choosing successively smaller elements of to produce a descending sequence. If the intersection of this sequence contains a point in, wins, otherwise, wins. If is any family of sets meeting the above criteria, then has a winning strategy if and only if is meager. Examples: subsets of the rails. The rational numbers are meager as a subset of the rails and as a space, that is, they do not form a bare space. The Cantor set is meager as a subset of the rails, but not as a space, since it is a complete metric space and is thus a bare space. By the bare category theorem, function space is the set of functions which have a derivative at some point as a meager set in the space of all continuous functions.